So there are lots of metabolic pathways that can occur in the cell. For example, maybe we want to take compound A and convert it into compound B, which then we want to convert to compound C, which then gets converted to compound D, which gets converted into compound E. However, in other situations, maybe the cell wants to take compound C and instead convert it into compound G, which then goes through this metabolic pathway. And in other situations, maybe we want to take compound B and convert it to compound J, which then goes through this metabolic pathway. So we can see there are lots of different potential metabolic pathways that can occur in the cell. However, let's say the cell specifically wants to go through this particular metabolic pathway. How does the cell force the molecules to go through this metabolic pathway? Well, to understand this, let's focus on this simple chemical reaction, taking compound B and converting it into compound C. So whenever we're trying to analyze a chemical reaction, there are two things to be aware of: the thermodynamics of the chemical reaction and the kinetics of the chemical reaction. And we know the thermodynamics is essentially related to whether or not this chemical reaction is energetically favorable. Taking compound B and converting it into compound C, is this reaction energetically favorable? AKA, does it have a negative delta G? Is this reaction spontaneous? But also we need to know the kinetics of this chemical reaction, which is essentially related to how fast is this chemical reaction. For example, maybe this reaction is thermodynamically favorable with a negative delta G. However, is it fast? Does this chemical reaction occur quickly? What are the kinetics of the chemical reaction? So first, let's focus on the thermodynamics of the chemical reaction. So therefore, if the cell wants to go through this particular chemical reaction, taking compound B and converting it into compound C, we need to make sure this chemical reaction is thermodynamically favorable with a negative delta G. So how do we make sure this reaction has a negative delta G? Well, we use ATP. So we know we can look in any old textbook and see that taking ATP and hydrolyzing it into ADP and inorganic phosphate has a standard state delta G of negative 32 kilojoules per mole. So therefore, this reaction has a standard state delta G of negative 32 kilojoules per mole. It has a negative delta G, so therefore we know this reaction is spontaneous. But it's important to realize what the standard state delta G means. That means that this reaction is specifically at standard state conditions with these standard state concentrations. Then under these standard state conditions, taking ATP and hydrolyzing into ATP and inorganic phosphate has a negative delta G of negative 32 kilojoules per mole. However, it's important to realize that this is an idealized, this perfect situation with these 1 molar concentration of all reactants and products. However, in the real world, for example, inside the cell, under these cellular concentrations, taking ATP and hydrolyzing it into ADP and inorganic phosphate has a non-standard state delta G of negative 68 kilojoules per mole. So it's important to realize under standard state concentrations, this reaction has a negative delta G of negative 32 kilojoules per mole. However, in these cellular conditions with these cellular concentrations, ATP hydrolyzing into ADP and inorganic phosphate releases negative 68 kilojoules per mole. So we can see it's the concentrations that determine how much free energy is released. So this is a really important point. It's the concentrations that determine how much free energy is released, the delta G. And under different concentrations, a different amount of free energy is released. And to really illustrate this point is, let's say we have this chemical reaction. And let's say this chemical reaction reaches equilibrium, because we know all chemical reactions with enough time will reach equilibrium. So let's say this reaction reaches equilibrium concentrations. So under these equilibrium concentrations, and again, ignore this. So under these equilibrium concentrations, because we know this reaction will eventually reach equilibrium concentrations. So once we've reached these equilibrium concentrations, taking ATP and hydrolyzing it into ADP and inorganic phosphate releases no free energy. And in fact, this is the definition this is how we define whether a reaction is at equilibrium. Because we know whenever a reaction reaches equilibrium and reaches these equilibrium concentrations, then the chemical reaction releases no free energy. So this really illustrates the point that it's the concentrations that determine how much free energy is released. And under certain concentrations, change how much free energy is released. But really what's important is these cellular concentrations, the concentration of ATP, ADP, and inorganic phosphate under these cellular conditions and the cellular concentrations. And the point is under these cellular concentrations, this reaction is very thermodynamically favorable. It has a very negative delta G of negative 68 kilojoules per mole. So therefore, under these cellular concentrations, taking ATP and hydrolyzing it into ADP and inorganic phosphate is very thermodynamically favorable with a very negative delta G. So even though maybe taking compound B and converting it into compound C, maybe originally it's not very thermodynamically favorable. However, if we can couple this reaction with the hydrolysis of ATP into ADP, then we can make this chemical reaction very thermodynamically favorable, because we know this reaction is highly thermodynamically favorable. So we can use the free energy of this reaction to push this reaction forward. And this is a way we can use ATP to push chemical reactions. For whatever reason, let's say we want to take compound B and convert it into compound C, we can force this chemical reaction by using up ATP, by using this hydrolysis of ATP into ADP. So therefore, the way you should think about it is we eat food. We eat carbohydrates and fats and amino acids and proteins, and we can use the energy in those molecules to create a lot of ATP. So therefore, we have these concentrations that allow this reaction to be very thermodynamically favorable. So now that this reaction is so thermodynamically favorable, we can use this chemical reaction, ATP hydrolyzing into ADP and inorganic phosphate. We can use this chemical reaction to push other chemical reactions forward. So that's how we make chemical reactions thermodynamically favorable. But now let's talk about the kinetics, which is telling us how fast a chemical reaction occurs. And every single chemical reaction has its own unique rate constant. And the larger the rate constant, the faster the chemical reaction occurs. For example, maybe taking compound B and converting it into compound C has a very small rate constant. So this chemical reaction has a very small rate constant. Therefore, this reaction occurs very slowly. However, maybe taking compound D and converting it into compound E has a very large rate constant. So if this reaction has a large rate constant, this reaction occurs very fast. And we know the larger the rate constant, the faster the chemical reaction. And every single chemical reaction has its own rate constant. And the larger the rate constant, the faster the reaction. The smaller the rate constant, the slower the reaction. So maybe this, taking compound B and converting it into compound C, maybe it's very thermodynamically favorable with a very negative delta G. So therefore, because this reaction is so thermodynamically favorable, it must occur very quickly, right? Well, no. Even though this reaction is very thermodynamically favorable, we already explained how it has a very small rate constant, so therefore it occurs very slowly. So this is very unintuitive, and it's important to dissociate these two concepts. Thermodynamics and kinetics are completely separate concepts. So even though this reaction is very thermodynamically favorable, it can be very slow. And even though this reaction is not very thermodynamically favorable, it can still have a very large rate constant, and if it has a large rate constant, it occurs fast. So now let's focus on this reaction, taking compound A and converting it into compound B. Maybe it has a very slow rate. Maybe this reaction has a rate of 1 nanomole per second, which means 1 nanomole of product is made per second. And that's what this rate is. And really, this is a bit of a simplification. Technically, rate is the way how the molarity of the product increases with respect to time. But for simplicity, we can define the rate of this chemical reaction by knowing how many moles of B is made per second. So let's say this reaction has a rate of 1 nanomole per second. That means 1 nanomole of B is made per second, and that's the rate of this reaction. So it's a pretty slow rate. Only 1 nanomole of B is made per second. However, let's say we have this exact same chemical reaction. Compound A converted into compound B, but now let's say we have an enzyme. So now let's say this enzyme catalyzes this chemical reaction and makes this chemical reaction occur much faster. So now maybe this reaction has a rate of 15,000 nanomole per second. That means 15,000 nanomole of B is made per second. 15,000 nanomole of the product B is made per second. So that's the rate. So clearly we can see when this reaction didn't have an enzyme, it occurred very slowly with this rate. However, once this same chemical reaction was catalyzed by this enzyme, it occurred much faster. So therefore we can see enzymes increase the rate of a chemical reaction. So therefore, enzymes increase the rate constant. Originally, this uncatalyzed reaction had a very small rate constant. However, this same reaction, once it was catalyzed by an enzyme, it had a much larger rate constant, so therefore it occurred much faster. So therefore enzymes increase the rate constant of a chemical reaction. And these enzymes are really important. So maybe initially this reaction occurred so slowly, it virtually didn't exist. It existed so slowly, it was negligible. However, once we activate this enzyme, now it occurs in a more meaningful rate. So now we know everything we need to know to understand how the cell pushes a particular pathway forward. For example, let's say for whatever reason, the cell wants to go through this particular chemical pathway, this particular metabolic pathway. How does the cell push this particular metabolic pathway? Well, what it does is it has to upregulate and activate these particular enzymes. For example, we activate this enzyme, so now this reaction occurs at an appreciable rate. So now we create a lot of compound B. So now once we form compound B, we can either form compound J, or we could form compound C, or we could form compound F. However, if we activate this particular enzyme, we know this reaction is going to occur fastest. So this reaction is going to occur. And yeah, this reaction is going to occur very slowly, but because there's no enzyme, this reaction is going to occur so slowly, it's negligible, and we can really ignore it, and we can ignore this enzyme. Because we can ignore this reaction, because we know this is the only enzyme that's activated, so therefore this is the reaction that's going to occur at an appreciable rate. And then we activate this enzyme, so this reaction is going to occur at an appreciable rate. And this enzyme's activated, and this enzyme's activated, so therefore we know this is the particular pathway that's going to occur. And something important to realize is that this is true for most metabolic pathways that you learn about in a biochemistry class. For example, glycolysis, or the Krebs cycle, or the pentose phosphate pathway. Most metabolic pathways, most of the chemical reactions are at equilibrium concentrations. For example, maybe this particular reaction, taking compound B and converting it into compound C, maybe this reaction is at equilibrium, and the concentration of B relative to the concentration of C are at equilibrium concentration, so therefore this reaction is at equilibrium. And the same thing with this reaction. The concentration of C relative to the concentration of D are at equilibrium concentration, so therefore this reaction is at equilibrium. And this reaction is also at equilibrium. So most reactions in the cell, most reactions in any metabolic pathway, most of the reactions are at equilibrium concentrations. And remember what that means. If this reaction is at equilibrium, if the concentration of C and the concentration D are at equilibrium concentrations, then we know by definition that taking compound C and converting it into compound D releases no free energy. It has a delta G of 0. And again, that's true whenever a reaction is at equilibrium concentrations, no free energy is released. Taking compound D and converting it into compound L, no free energy is released, so there's no energetic incentive for this chemical reaction to occur. So all these reactions are neutral. They're kind of apathetic to which way it goes, because again, this reaction is at equilibrium concentration, so it doesn't care which direction it goes, because either direction releases no free energy. However, what we can do is we can activate a very specific enzyme. For example, let's say we activate enzyme X. So let's say we activate this very specific enzyme which couples this chemical reaction with the hydrolysis of ATP into ADP. And we already explained the cellular concentrations of ATP and ADP are in such a way that allows ATP hydrolyzing into ADP to be very thermodynamically favorable. So if we couple the hydrolysis of ATP with this chemical reaction, then we know this chemical reaction is going to be very thermodynamically favorable. So now we know compound A is very going to be this compound A into compound B. This reaction is going to be very thermodynamically favorable with a very negative delta G. So what does that mean? That means this reaction is going to be very thermodynamically favorable, and because we have an enzyme, we know this reaction is going to occur very fast. So those are the two ingredients. This reaction is thermodynamically favorable, and it's also going to occur very fast. So this reaction is going to push this entire metabolic pathway forward. So how does that happen? Well, if this reaction is so thermodynamically favorable and occurs so fast, this reaction is going to occur very quickly, so therefore we're going to create a lot of B. So what happens when this reaction occurs a lot and creates a lot of compound B? That's going to ruin these equilibrium concentrations, because we know originally this reaction B and C was at equilibrium concentrations. So therefore, if this reaction occurs a lot, we're going to create a lot of compound B, and that's going to throw off these equilibrium concentrations. So now we're not at equilibrium concentrations. This reaction goes forward, we create a lot of B, so now we have relatively more B than is at the equilibrium concentrations. So now that we have relatively more B, now we're not at equilibrium concentration, so now this reaction is going to be thermodynamically favorable. We're not at equilibrium concentrations because, again, this reaction keeps going forward, creating a lot of compound B. So now we have relatively more B. So now we have concentrations that allow this reaction to be thermodynamically favorable with a negative delta G of negative 10 kilojoules per mole. So now this reaction is thermodynamically favorable and is going to go forward. And now that this reaction goes forward, now we're going to create a lot of compound C. And now that we create a lot of compound C, now this reaction isn't going to be at equilibrium concentrations anymore because this reaction will go forward. So now we have relatively more C than the normal equilibrium concentrations. So now that we have relatively more C, now this reaction isn't at equilibrium concentrations anymore. We have relatively more C, which is now going to make this reaction thermodynamically favorable with the negative delta G, which again is now going to make this reaction thermodynamically favorable because now that this reaction is thermodynamically favorable, we're going to have more D relative to the original equilibrium concentrations. So again, now hopefully you can see the pattern. Now that we have more D than the normal equilibrium concentrations, that's going to push this reaction forward. And now that this reaction is pushed forward, now we have relatively more L than the original equilibrium concentrations, which is going to push this chemical reaction forward. So the point is, we activate this enzyme, which is coupled with the hydrolysis of ATP, which strongly pushes this reaction forward, which ruins these equilibrium concentrations, which essentially pushes this reaction forward in this particular pathway. And now that we have these enzymes activated, that's going to allow these chemical reactions to occur in a timely manner. And really, this is just another way to look at Les Chatelier's principle. And we know what Les Chatelier's principle is. If you increase the concentration of B, that's going to push this reaction forward. If you increase the concentration of reactants, that's going to push the reaction forward. That's Les Chatelier's principle. And that's essentially what's going on. Because again, we said this reaction is very thermodynamically favorable, so it's going to strongly go in this direction. So now we're going to create a lot of compound B. Now that we create a lot of compound B, that's going to push this reaction forward towards compound C. That's Les Chatelier's principle. If we create a lot of compound B, that's going to push this reaction towards compound C. So again, this reaction is very thermodynamically favorable, creating a lot of compound B. Now that we create a lot of compound B, that's going to push this reaction forward towards compound C. That's Les Chatelier's principle. Now we create a lot of compound C, which is going to push this reaction forward. And now we create a lot of compound D, which is going to push this chemical reaction forward, and etc. So now let's say we want to go in this reverse direction. Let's say we want to, for whatever reason, the cell wants to take compound I and go in this reverse direction, forming compound A. So how do we do this? Well, again, remember, most chemical reactions are at equilibrium with any metabolic pathway. Again, like glycolysis or lipolysis or beta oxidation or any metabolic pathway, fatty acid synthesis, any metabolic pathway, most of the chemical reactions that create the metabolic pathway, most of the chemical reactions are at equilibrium, and most chemical reactions in the cell are at equilibrium concentrations. However, what we can do is we can activate a completely separate enzyme. Let's say we activate this enzyme Y, this completely separate enzyme that's designed in such a way that it allows the hydrolysis of ATP into ADP to be coupled with this chemical reaction, taking compound B to form compound A. So now that we have this unique enzyme that's coupled with hydrolysis of ATP, now this reaction is very thermodynamically favorable with the negative delta G. So therefore now this reaction is going to go strongly forward. So now that this reaction strongly goes forward, now we have very little B because this reaction is strongly going forward. So all the B is being used up, converted into A. So now that we have little B, that ruins the equilibrium concentrations of this reaction, which will push this reaction forward, which will ruin the equilibrium concentrations of this reaction, pushing this reaction forward, and etc. So because this reaction is going so strongly and is so thermodynamically favorable, that's going to really push this whole pathway in this direction. And again, because these particular enzymes are activated, and we're going to have to inactivate all these other enzymes, and because these these enzymes are activated. So now this reaction is going to strongly go forward. So this reaction being so thermodynamically favorable, strongly going in this direction, is going to push all these reactions forward because we have these enzymes activated. And again, this is just another way of looking at Le Chatelier's principle. We know if we decrease the concentration of a compound, that pushes the reaction forward towards that direction. So therefore, if we decrease the concentration of B, that's going to push this reaction towards B. And that's exactly what's going on. We explained how this reaction is very thermodynamically favorable, taking a lot of B and converting it into compound A. So therefore, this reaction is very thermodynamically favorable. So we have very little B, which is going to push this reaction forward towards B. If we have very little B, that's going to push this reaction forward towards B. So again, this reaction strongly goes. So we have very little B, ruins the concentrations, pushes this reaction forward, ruins the concentration of this guy, pushes this reaction forward, and this is just another way of looking at Le Chatelier's principle. So I know this is really an abstract and advanced concept. So in the next video, I'm going to go over a real-world example with glycolysis. So glycolysis is when we take glucose and we do a bunch of chemical reactions, eventually forming pyruvate. But again, with any metabolic pathway, we know most of the chemical reactions that make up the metabolic pathway are at equilibrium. This particular reaction is at equilibrium. The concentration of this guy relative to this guy are this reaction is at equilibrium. So in the next video, I'll go over a real-world example.